Hello, everybody. Welcome to a new topic, topic 14 in ISCN 630, Human Operator in Complex Systems. This topic is on biomechanics and how humans use our musculoskeletal system as a machine, biomachine, to produce work, and how that plays out in the industrial setting, in the work environment, right? Okay, so subtopic 1, manual material handling as a task that's associated with a lot of work domains, and occupational biomechanics. And this is about the study of how humans use our biomachines to produce work in occupational settings. Okay, so first of all, there are a large number of work domains that involve some form of producing work, moving material, pushing, pulling, lifting, carrying, squeezing. And when we can study in the previous topic, work physiology, where we talked about how energy is produced through metabolism, through internal sources, we're also now talking about, well, now we have the simple machine, of a bone connected to, a torque source. And so now we can talk about using, the full dimensions of the musculoskeletal system to produce all of these forms of physical work. All of them involve contractions of skeletal muscles, controlled different muscle groups, for example. But ultimately, it all breaks down to an energy source causing a contraction, and then the machine of the human body able to produce, transformations of that force into producing work. All right. So the factors, how well do we, produce, or how well do we perform these sorts of tasks? Physiological, we just talked about topic 13, work physiology, how energy is generated within the body. Psychological factors, so things like motivation. If there was, if you, ever did a team sport and part of that is getting psyched up, we do have the ability to produce greater amounts of force when we're in the right psychological mindset, when we use, motivational factors. And then biomechanics, and again, I'm talking about, basically applied statics and dynamics to the machine of a human body. All right, so again, many different work contexts, different occupations involve manual material handling. There are some where it is the main reason there's a human. Maybe at some point in the future, these sorts of tasks become automated. That's a good thing. It doesn't, it does mean that, certain jobs become obsolete, but a different way of looking at it is a certain type of human activity becomes obsolete while those jobs still remain, and humans are just inflicting less damage to their bodies, for example. But as things stand right now, humans are designed to be biological machines, and so we produce work with those machines. And almost any industry, you're going to find some form of people got to carry, I got to carry my office equipment to the coffee room. That's manual material handling. So any, roughly any industry. All right. Now, why is this an important thing to study here? Not just for the, health and well-being of our fellow human workers, but also because of the costs associated. So, if we're looking at it from that systems perspective, yeah, we want our workers to be happy, but we want our workers to be happy ultimately so they do good work, so our business is cost effective. And costs creep in when workers are not performing physical tasks in a healthy way, or in ways that would lead to injuries. Injuries on the job are really going to be, the liability is the company, and so they're going to be paying workers' comp. They're going to be paying indirectly for, not having that worker there to, perform the work. But yeah, just on at least on a national scale here, a significant portion of injuries in industrial settings involve somebody trying to move something. A lot of issues with back, like the proper way to lift is not bent over at the back. We're gonna, do a little bit of math to show the extent to which that is problematic to bend over like that. But this was 20 years ago already, but about $50 billion annually, as part of at least the United States economy is lost, due to injuries in the workplace, the compensation that comes from that, lost work time, et cetera, long-term health, needs that maybe are now going to be absorbed by, the company and the patient and their family. So, it's a big problem. 60% of overexertion injuries involve the back. So that is our most, let's say, our most vulnerable position as we age and still think, we're strong enough to do this and we don't have proper form. That's when we have these, tend to have lower back injuries at a higher rate. Okay. So I mentioned, this subtopic is about manual material handling, the task, but it's also introducing the field of occupational biomechanics. And we have a professor, Dr. Zhudong Zhang, who is a specialist. His area of specialty is occupational biomechanics. And, he trained with these scientists here, Dr. Chaffin was, was still at University of Michigan when I was there as a grad student, and Dr. Martin was on my committee actually. But in any case, this is its own field. You can take a course in this. Dr. Zhang frequently offers a standalone semester course in occupational biomechanics. So if this stuff is interesting to you, definitely look into that. But yes, so again, this is the science concerned with the mechanical behavior of the musculoskeletal system and component tissues when physical work is performed. I think I've said that, that definition about 8 different ways so far in this one lecture. So I hope you get the point. Humans are machines, and they're using them to perform work in an occupational setting. Okay, so if this starts to look like, your statics and dynamics or physics classes, yes, that's where we're going with this. This is mechanics modeled, but using the human body as the machine, statics and dynamics, right? All right. So here is, the structure that we're talking about here, and the and the motor, so to speak. So our musculoskeletal system together combined. So the skeleton works with the muscles to produce movement and repositioning and work. So, all together supports and protects the body, maintaining our posture and any sort of controlled movement. Also, generation of heat. So our metabolism, our general, entire biological system depends on body heat at a certain temperature. A lot of that heat is generated via metabolism and basically the friction that's released from the contraction of muscles. So a lot of our internal heat energy, comes from our muscles, our muscular system here. We want to recognize the different subcomponents here, the includeds in this system. So bones, ligaments, tendons, cartilage, and fascia are all different types of connective tissue. So yes, bone is considered a connective tissue. Basically, this is anything that, it's our internal structure and it holds everything together. The muscles are the motors, right? The muscles are capable of movement, of installing, or of applying force to move, the different segments of the body that are connected. A joint is when there's a union of 2 or more bones, and a lot of times there's, ligament, tendon, cartilage, fascia, connective aspects, at those joints. All right. Muscle strength is something that, again, it depends on physiological factors, psychological factors, and biomechanical factors. So, did you eat your Wheaties? Are you are you really motivated to really grip this, like you're doing a love test or something, you know? And do you have the right grip to produce the maximum amount of force given the machine, you know, of the complex biomechanical machine of our different limbs, right? So it's really difficult to say this muscle, you know, my grip strength is involving probably, I don't know, 10 different muscles at least, right? If not more, probably a lot more, I don't know. But how do I say what's your strength in that muscle? Really difficult. So you have to kind of infer, you know, from exterior sorts of behavior. You know, a very common one is the grip strength test, and that's used as sort of our consistent standard, you know, to you know, is how much force can somebody put out. But again, of course, it's dependent on so many different factors. But in general, these are things that can be recorded and tallied and, you know, kept in a data set, just like, you know, the anthropometric methods that we went through in topic 10, I think. Right, no, topic 11. All right. So yeah, here we go. You know, we can determine the strength data, you know, what is the 50th percentile force output for various, you know, joints and limbs. So for example, forearm flexion and extension, 276 newtons is your 50th percentile for a male worker. So that could be used in the design of things, and women 160. Again, these are gross simplifications, but they're based on, you know, large pools of data that spawn these span these demographics. So yeah, so this is where it might matter, right? So the average adult male, let's say, you know, can produce 14.1 Newton meters when turning a handle. So if this is a machine, you know, this engine block here, if this is something that is designed for a human to be able to interface with for maintenance reasons or whatever, that's your torque limit if you're going to have your average human able to do that, right? If you want enough force to have a reasonable adult open the aircraft door and not a curious child, you require a certain amount of force in order to, you know, to operate this sort of a lever. And so these data can help, you know, with that sort of design standard. You know, when is it an acceptable level of tension? So for example, I always start the lawnmower at our house. My wife, I'm sure she could do it, but given our history with lawnmowers, it's usually one that requires a lot of pulls or a lot of extra strength. And so, yeah, that could be a design standard, you know, where, you know, what is an acceptable amount of, I guess, torque, or I'm not, which if you're pulling a string, I guess it's just a, you know, linear force. But, you know, what's an acceptable, you know, Newton meter threshold there. All right, there we go. Okay, so just, you know, high level things, if you have a workplace, with manual material handling. Oops, go back. There we go. You know, just first of all, as I mentioned, you know, our workplaces are increasingly automated. They're increasing, you know, sophisticated machines that can replace the need for humans to produce work with our fragile biological bodies. So by all means, you know, this is our greatest advantage. Let's use the machines around us to produce the force as much as we can. So if you can find a way, you know, to relieve the human as the main source of the work in terms of force over distance, you know, look at ways to make it less problematic biomechanically for a human body. So reducing the size, the weight, you know, the size, even if it weighs the same, depending on how big it is, you know, it's going to dictate what my grip is. That's going to determine, you know, that's going to affect the amount of strength I have and the amount of effectiveness and the amount of torque I might have at my back muscles, which is where, you know, once you're in your middle ages, you start to wear out that back. You know, what the handholds make a big difference in how much people can support. You know, no twisting. Twisting is particularly problematic. You'll see in a later subtopic. There are mathematical representations for if a lift involves any sort of pivoting like this. Bend at the knees as much as possible, not at the hips, so keeping the trunk upright. Minimize a carrying distance. When I walk while I'm maintaining a load, I am, I have a certain level of strength being exerted in a static way in my upper body, but my lower body is trying to move. And this is, a recipe for, clenched muscles up top and varying muscles in other places in the body. It's a recipe for a potential, pulled muscle or something like that. So minimizing carrying distance when you are exerting force. Translate horizontally, not vertically. If I've got to take this load from station A to station B, it's great if that is a lateral movement as opposed to I got to lift and put it up or lift and, or drop it down. Keep the movement smooth. Any sort of jerking motion is more likely to lead to injury. So you want to have controlled movement. To think about, do I need to, from station A to station B, do I have to move around a barrier? That requires, more sophisticated, sorts of controlled while exerting maximum force movements. And that could be a problem. This is industrial engineering 101, but if you find there are multiple steps in a let's say a process, a manufacturing process, where I got to take my workpiece off the ground, put it up on my workbench, work on it, and then there's a later step where I take it back off and put it down. Those are two wasted movements. If we can find a way to just have that piece, be at a common elevation, so to speak, for all the work that needs to be done. So if you can find a way to eliminate a lift and a lower step and keep the workpiece or keep whatever the load is from needing those two vertical movements, that's good industrial engineering. All right, so I previewed this slide a few times accidentally, but these are just examples of equipment that can be used to assist, increasingly in environments where humans are major manual material handling domains. This is an example of a lift table. Don't make the humans produce that. A forklift truck. This would be obvious. Don't. And I even, it makes sense to use a forklift truck to lift almost anything if you're doing it repeatedly throughout the day. So even like, I've just got, for example, I've been doing some landscaping recently, and I've been hauling the bags of mulch, and whatever they are, I don't know, 40 pounds or something like that, or maybe probably, I don't know that they're that much, but they're heavy and they're a pain in the butt. And I have had a time in my life where I would try to carry two of them at a time, and I was really super strong about it. And then when I go to purchase more of them, I noticed that no matter how many I bought, one of the workers there would always load it into the car using the fork truck. And I thought, see, that's really smart. Like, it could be real easy to just grab a couple off the thing, but well, I guess, probably if it was just a couple, you would have just grabbed them off the pallet. But yeah, anything that was reasonably, can I just save my back from one more bend over and lift? If in the workplace, it makes sense to invest in a large machinery like this sometimes for even those small loads. All right, so anyway, yep, I mean, all kinds of different mechanical aids, cranes and hoists can be used to support weight so that humans don't need to. These examples here are working parts dispenser. This is kind of about not minimizing the amount of movement you may need in a workspace that is human powered with a load. Okay, so having things kind of fed directly to you instead of having to move to them. A gravity chute is we can use, we're not costing a lot of additional energy for this sort of gravity chute. It automatically feeds through here, so we can move things that way. Rollers, this is a great way to support horizontal translational support with I don't have to support it this way with my muscles. I can just ease it along this sort of a roller path. All right, very good, thanks. That's the end of this chapter.